Welcome to Plutus IAS, and today we are covering particle in one dimension box. So, particle in a 1D box, we already know that it comes under the category of the quantum mechanics when we study atomic structure. So, what does particle in 1D box means? So, particle in 1D box, you can assume that this is a carbon bond. Okay, now let's create a box around it, assuming that this is a box centered around the carbon bond. It has some length 0 and let's say around some length L. So now if you remember, whenever we talk about resonance, the electrons are circulating between these positions. Now currently I'm assuming that the electrons that are moving within this space, it can only move within the length 0 to L. Why? Because beyond it there is nothing further that can carry that electron. So outside of this box we are assuming outside of this box we are assuming that the potential is infinity, that you require infinite amount of potential so that we can take this electron and can take it out, and same will be on the other side. Inside this box the potential is 0, that means this electron can freely move around it. Okay, now using this analogy, now let's remove the carbons, since now we have understood what does this box actually defines in the space. So the conditions we have, this is the pose, this is the length L and 0. They are called as our boundary conditions. These are our boundary conditions. Now since this electron cannot exist anywhere apart from this definite length, we can say that outside of this box the wave function which defines the motion of this particular electron or any particle, it will be 0 where at boundary conditions. So now with all of that in the place, let's move forward. Okay, in the place, let's move forward. So first, what do we know about? We know that the Schrodinger's wave equation is given by del square psi plus 8 pi square m h square e minus v equals to 0. Now here this del operator also goes by the name of Laplacian operator, which is a culmination of three different wave functions. Which is d by dy, d by dz. Now since I'm considering particle moving in only one direction, I can assume all these functions to be equals to 0. So I can switch this into n, convert it like this. This is my final wave function in double square. This is my wave function using Schrodinger's wave equation. Now later on, since we have assumed that the potential is 0, this equation can further be written as d square psi dx square plus 8 pi square m e psi divided by h square. Now let's assume all these constant value, which is mass, energy, Planck's constant, everything is constant. Let's assume it to be equal to a constant alpha square. Now if I rewrite this equation looks like this: alpha square psi equals to 0. Now this equation is a very special type of differential equation. Now the solution to this is very typical, and we are directly utilizing the result, and it is given by the formula. The wave function psi will be given for this equation equals to A E iota m alpha plus B E minus iota m alpha. Now, using Euler's theorem, it can be further simplified as A sine alpha x plus B cos alpha x, whatever factor we are putting in. Now, we have considered the box of the length as 0 to L. That means this x is the confined space in which this electron can be moved. So, x is equals to what? X is equals to length of the box. So, now applying boundary conditions, applying boundary conditions where putting x equals to 0, it will be equals to alpha a sine alpha multiplied by 0 plus b cos alpha multiplied by 0. Now, the cos alpha equals to 1 while sine alpha will become 0. Now, at boundary condition, since we have already proved that the particle cannot exist outside of this box, we can simply write that the psi would be equals to 0. So here the psi will be equals to 0. So in this equation, we will find that B will be equals to 0. So that means this entire equation is only in terms of A sine alpha x. A sine alpha x. Now, moving forward, we know that the alpha square we have taken as 8 pi square m e upon h square. 8 pi square equals to h square. This value, and also we know that this function a sine alpha x is in terms of sine, and sine function repeat its value after regular intervals. This we already know. So applying the now applying the secondary boundary condition where I'm assuming the x is equals to L. So now at second boundary conditions, the alpha will be equals to 0. It will be sine alpha x. Now since sine is repeating its value after every interval of what? First it will have value of 0, then at pi it goes again 0, then again at 2 pi, then at 3 pi. So that means this wave function will always be a multiple of n pi. So here n pi is what? Is the angular portion. Comparing it, alpha x equals to n pi. Alpha is n pi, x is equals to length of the box. Now I need the value of alpha square. It is n square pi square L square. And also alpha is equals to what? 8 pi square m h square into E. So when you solve this, we get the energy equals to n square h square 8 m L square, and this is the energy of the particle in one dimension box. Now we have found the energy, but still we haven't found the value of this wave function a sine. Now alpha we have already proved equals to n pi x upon L. We don't know the value of this constant a. So we will normalize the function. Applying the normalization condition, it will be a square sine n pi x l, limiting condition 0 l, and it will always be equals to 1 if this is a, because probability density will always equals to 1 because within the confined region the particle should be there. Okay, so there will always be a possibility of particle existing within this range as per the boundary condition. So when you solve it, it will be sine square n on multiplication of both sides. It will give you a square by 2, and the integration of sine square x will be given by x. You can directly utilize that whenever you encounter a function of sine square bx time, its integration will always be equals to x, whatever the limits you are given, plus 1 by 4b sine 2bx with the limits. Now, since I am taking the value 0 to L, at the boundary condition, this portion will be eliminated. So, we are only left with a square 0 to L, a square by x 0 to L divided by 2 equals to 1. On solving, it is a square x upon 2 equals to 1. So, the value of a comes out to be 2. X is equals to what? Our length L, it will be 2L square. Here the value of a will come out to be under root 2L. So summing up everything, this is the wave function for a particle moving in 1D box. This wave equation gives us all the information which is required to define the motion of the particle. Okay, remember, it has no physical significance. Apart from that, it describes the motion of the particle. To find more information regarding that particle, we need to find probability density. So I hope this would have cleared all your doubts regarding your particle in one dimension box, and you have learned something new. In case of any doubts, you can add it to the comment section and we'll get back to you. Thank you for joining us.